What's up, mathematicians? Justin here, and in today's video we'll be talking about the concept of similar triangles. Let's start out by recalling the measurement activity that I proposed in the previous video. If you did the activity, I want you to stop and think for a minute. In fact, pause the video and write down some ideas in response to this question. What implicit assumptions did you make in order to complete the measurement activity from the previous video? Okay, so let's look at that activity where I asked you to find the height of some tree or some other tall object without measuring it directly. So let's go ahead and just draw in a diagram here. So we've got our tree. Okay. And now this is not the only way that you could go about solving this problem, but I would say it's the most common approach that students come up with when I give them this problem to do in class. So the idea here is, because the tree itself is too tall to measure, you pick a reference object. It could be a person, it could be like a fence post, a water bottle, something like that. In this case, we'll put a person in. So we have our person here, and your reference object has the advantage of being directly measurable. If it's a person, maybe they already know how tall they are. If not, you can just take a tape measure and figure it out. So let's go ahead and imagine that this person, who is our reference object, is 1.6 meters tall. Now, the idea here is that whether you realize it or not, we actually have a couple of triangles that are formed by the two objects, the tree and the reference object, the ground, and this ray of light coming from the sun, or maybe rays of light plural coming from the sun. So here's our sun up here, shining down, making shadows. All right, let's go ahead and say that the length of the shadow of the person is 2.4 meters. And let's imagine that the length of the shadow of the tree is 25 meters. Of course, you would put whatever measurements you got in that situation. Now, the thing we don't know, of course, is the height of this tree. So let's put x in for that. X is typically what we use to represent some quantity that we don't know. Now, if you look at this situation and think about what's going on here, you may, the idea may come to you that it makes sense that the ratio of the height of the person to the length of the person's shadow, shouldn't that be the same as the ratio of the height of the tree to the length of the tree's shadow? Well, it's not. We haven't proven that that's true. And it's not necessarily logically necessary or obvious, but it certainly seems to make sense that those ratios would be the same. So let's go ahead and go with that. Let's take that approach and say that, okay, let's write the ratio of the person, so 1.6 to the length of their shadow, 2.4, and we'll say that that is equal to the height of the tree, x, to the length of the tree shadow, 25. Okay, now we have a nice little algebraic expression, and we can solve for x. We'll cross multiply first, and so we have 1.6 times 25 is equal to 2.4x. All right, now we want to get x all by itself. So we'll divide both sides by 2.4, divided by 2.4. So these will cancel out. 2.4 divided by 2.4 is 1. Now let's go ahead and pull out our calculator. So this is my original calculator that I used when I was in high school over 20 years ago. Still works great. Let's go ahead and plug these numbers in. 1.6 times 25, and then we're going to divide that by 2.4. All right, and I get 16.6 repeating. I'll round that to 16.7. So x, the height of the tree, is 16.7 meters, approximately. In fact, I should use the approximately equal to symbol. So I'm definitely rounding here. And because, you know, my measurements might be off, and maybe we're not even 100% sure that this method is correct, at least at this point. But that seems like a reasonable estimate for the height of the tree. So what does this have to do with similar triangles? Well, let's go back to the idea of the assumptions that we're making when we did this. So I asked you earlier in the video, what implicit assumptions did you make in order to complete this activity? Well, if you took the approach that I just laid out for you, the approach that uses a reference object, you are assuming a number of things. Some of the things you're assuming are that the tree and the reference object are perpendicular to the ground. In other words, they make a right angle with the ground. A second assumption you're making is that the ground is flat. And a third assumption that you may not realize is you're assuming in a way, or you have to assume for this approach to work, that the two triangles have all corresponding angles equal. So if we go back to, whoops, sorry about that. Still learning how to use this program here. But yeah, let's look at these triangles here. We have two right angles, the reference object here on the tree here, perpendicular to the ground, at least from the point directly below the highest point on those objects. And then this angle here, in this case, we had them lined up, but you could have it in a way that they're not lined up in that way. And this angle with the ground that the sun ray is making with the ground would have to be the same in both. And then we have the idea that these angles up here are also the same in both. Now I want to be clear that this is an assumption. We are assuming it's possible to have two triangles of different sizes in which all corresponding angles are equal. We call those types of triangles similar triangles. Okay, so here are a couple important facts about similar triangles. First of all, triangles which have all corresponding angles equal but are not the same size are similar. This is just the definition of similar triangles. A second fact that we're going to be talking about today is the fact that if two triangles are similar, then their corresponding sides are proportional. Now that is a theorem. It isn't part of the definition, but it turns out it will follow from this definition of similar triangles having all angles equal but different sizes. So let's look at an example of this. Actually, first let's look at how we can express this fact about proportionality algebraically. I've drawn here on my paper two similar triangles, and we'll call the first triangle A, B, C. We'll call the second triangle D, E, F. And we're going to go ahead and say that the angles B and E are the corresponding angles that are equal. A and D are equal, and C and F are equal. In fact, I'll just indicate that with these little arcs. D and A are equal, F and C are equal, and then angle B is equal to angle E. So this is, these two triangles meet the definition of being similar. They have all corresponding angles equal, but they're not the same size. So this fact about proportionality can be expressed algebraically as follows. The length AB divided by the length DE is equal to the length AC divided by the length DF, which is equal to the length BC divided by the length EF. Now, the way I drew it, I made the second triangle twice as big as the first triangle. So in this situation, all of these ratios would be 1/2. Length 1 to 2, length 3 to 6, length 8 to 16. Whatever those lengths are, the ratio of this length to this length is 1/2 for all of these sides. So now let's look at an example of how we can apply this rule of proportionality. And I'm just going to go ahead and say that this length is 10, and this length is 12, and this length here is 24, and this length here is x. Now, keep in mind that the way I've labeled it here, these are not to scale. The way I drew it, they're twice as big, but the way I've labeled it here, you can see I'm not following that. I'm just showing you how we can apply this rule of proportionality. So we'll say this is example number 1. And so let's take this length here, length 10, to this length here, 24. And this is equal to this length here, 12, to this length here, x. Okay, now we can cross multiply, and 12 times 24, that will give us 288. And then 10 times x, that will just be 10x. Now, in order to solve for x, we just divide both sides by 10, and we'll see that x is equal to 28.8. So, in the case where these two triangles were similar, with these corresponding angles equal, and this length here being 12, this being 10, this being 24, and this being x, this length x would have to be 28.8 units long. Now let's look at a situation that's a little bit more involved in terms of the algebra needed to solve it. So I've got these two triangles here, and I'm going to say that these are at right angles to each other, so those angles are equal. I'm going to say that these small angles here are equal, and that these upper angles here are also equal, meaning that these two triangles meet the definition for similar triangles. All the corresponding angles are equal, but one of them is bigger than the other. They're not the same size. Now I'm going to say that this length up here is 6, and this length here is 8. This length on the bottom of the bigger triangle is equal to 3x, and this length on the bottom of the smaller triangle is 2x minus 2. And the thing that I want you to try to figure out is this length here, the length of the bottom side of the larger triangle. If you want to try to solve it right now on your own, go for it. You can pause the video and give it a shot. But I'm going to go ahead and go through it with you as our second example. Okay, so first of all, we know that we can use this rule of proportionality because these two triangles are similar triangles. Let's look at the bigger triangle. The length of this side is 6 plus 8. So let's see, 6 plus 8 is 14. And the corresponding side on the smaller triangle, that's going to be length 8. Now, the length of the bottom side of the bigger triangle is 3x. And on the smaller triangle, we have the corresponding side, 2x minus 2. So we can cross multiply, and we have 3x times 8, that's 24x. And let's just write this as 14 times 2x minus 2. So we're not doing too much in our head. Sometimes it's easy to make a mistake when we do too much in our head. Let's distribute this 14, and we get that 24x is equal to, let's see, 14 times 2x is 28x, and 14 times negative 2 is negative 28. So now we can, we want to get x by itself, basically. You might be able to see what x is going to be just by looking carefully at this equation, but I'm going to go through the steps. I'll add 28 to both sides. Actually, I should write that more off to the side because I'm going to do both steps at once. So I'm going to add 28 to this side as well. I'm going to subtract 24x from both sides. And these two terms will cancel out, and these two terms will cancel out, and I'll be left with 28 is equal to, well, let's see, 28x minus 24x is 4x. Well, 4 times x is 28. That means x must equal 7. Okay, so if x is equal to 7, and the length of this bottom side of the larger triangle is equal to 3x, well, 3 times 7 is equal to 21. So the length of that side is 21 units. All right, that will wrap up this video, and in the next video we'll look at how this idea of similar triangles can lead us towards our study of trigonometry. We'll see you then.